Welcome to this explainer. Today, we're doing something a bit different. We're looking at math not as this rigid set of absolute rules, but as something far more fluid, dynamic even. We're going to explore how adding literal brushstrokes of uncertainty into rigid mathematics is actually helping us paint a much clearer, more accurate picture of our incredibly complex world. I know, it sounds totally counterintuitive, right? But stick with me. By the time we finish, you'll see exactly why embracing the unknown is a total game changer for solving some of our biggest scientific challenges. So, let's dive right into this big question. What actually happens when you inject uncertainty into the world's most rigid math? We're going to answer this by looking at a rapidly growing, honestly fascinating field called probabilistic numerics. Historically, right, when we use computers to solve intense math problems, think complex differential equations or integrals, we expect a single precise answer, a strict number. But the real world, it's not strict. It is noisy, it's chaotic. Probabilistic numerics completely flips the script on this paradigm. Instead of pretending our numerical calculations are 100% perfect, it treats the calculation itself as a best guess, generating a probability distribution that honestly says, hey, here is our best answer, and here's exactly how uncertain we are about it. And as we're about to see, applying this concept is fundamentally changing how we build and interact with the real world.
And the sheer momentum of this research is just undeniable. Look at the explosion of this field from its first major conference in Sophia Antipolis, France, back in September 2025, to the second one in Finland just a year later. If you track the publications in the Proceedings of Machine Learning Research, it's wild. In Volume 271 from 2025, the foundational ideas were really just taking shape. But by Volume 341 in August 2026, the research aggressively pivots. We're talking a massive leap from pure theoretical foundations straight into real-world applications. We are basically moving out of the chalkboard and directly into the field.
Which brings us to our first major applied applicated area, aerospace and engineering uses. To really get how this is applied, we've got to define a core tool first, statistical finite elements. Now, if you're an engineer, standard finite element analysis is your bread and butter. You take a really complex shape, say a car chassis, and you break it down into thousands of tiny, simple mathematical pieces or elements to calculate exactly how force affects them. But what if the manufacturing wasn't perfect? What if the steel has microscopic flaws? Statistical finite elements steps in and blends that numerical modeling with probability. It basically means the mathematical blueprint itself now understands and accounts for its own real-world imperfections.
And the applications here are incredibly practical. There's a brilliant 2026 paper by Rogers, O'Connell, and Champneys, where they take all that dense theory and apply it directly to physical vibration problems. Because if you're building a bridge, a skyscraper, or a jet engine, vibration is pretty much your worst enemy. By using probabilistic numerics, these researchers aren't just taking a shot in the dark at how a structure might vibrate. They're providing a highly measurable range of uncertainty for those vibrations, which gives engineers a vastly more robust safety margin. I love this comparison because it highlights a massive gap. You have cold, abstract mathematical modeling on one side and the messy, often dangerous reality of structural engineering on the other. This math isn't just sitting isolated in an ivory tower, it's specifically designed to handle the unpredictable physical world where relying on standard rigid equations could literally lead to catastrophic failures. It's a perfect encapsulation of why this field matters so much.
We actually see this applied again in aerospace, where a team from the Finland conference used physics-informed machine learning to reconstruct wind turbulence from a moving aircraft. This paper by Ketmas, Pernet, and their team tackles an incredibly tough problem. Just imagine you're flying a plane. You're moving fast, the air around you is totally chaotic, and you're trying to use LiDAR, lasers basically, to map the turbulence ahead of you. Because both you and the wind are moving unpredictably, standard math just chokes. But by injecting probabilistic models that respect the actual laws of physics, they can accurately reconstruct that turbulence. It's like they're literally painting a clear picture out of invisible, chaotic air. Absolutely wild.
All right, let's shift scales for a second and look at computing and neural dynamics. To understand this jump, let's look at another foundational brushstroke in this field, Kalman filtering. If you have ever used your phone's GPS to navigate through a dense city, you have directly benefited from a Kalman filter. Basically, it takes a series of noisy, imperfect measurements over time, like your phone desperately bouncing signals off satellites between tall buildings, and mathematically zeroes in on exactly where you are. It is inherently probabilistic. It deals with all that noisy uncertainty to find the hidden truth underneath. Now, take that concept and apply it to the human brain.
Researchers Hummel, Wenger, and Cunningham did exactly this by making the common filter computation-aware to decode neural dynamics. Look, the brain is the ultimate noisy system, right? Neurons are firing in these massive, chaotic patterns all the time. Decoding those signals takes an immense, almost unfathomable amount of computing power. By applying advanced probabilistic numerics here, these scientists are much better at separating the actual signal from the brain's background noise. It's letting us decode what the brain is doing in real time, all while managing that massive computational load. It's an absolutely stunning application of mathematical uncertainty to human biology.
And it's not just brain science. We're seeing these algorithms directly optimize highly technical computing fields across the board. You've got researchers using conformal probabilistic numerics for adaptive edge cloud offloading, making data transfer way more efficient. Others are using amortized Gaussian process inference or scaling up probabilistic simulators so they can handle insanely complex equations without crashing. The big takeaway here? Embracing uncertainty is actually making complex computing exponentially faster and more reliable.
Okay, let's go even deeper. Let's talk about decoding the literal building blocks of physics and chemistry.
What's really fascinating here is how researchers are aggressively pairing these highly complex theoretical methods with very specific real-world targets. The theory isn't just living in a vacuum anymore. For example, back at the 2025 conference, Poot and colleagues used the random mesh finite element method to target inverse problems, which is basically playing detective, working backward from an end result to figure out the cause. We're also seeing methods like guided particle diffusion sampling being mapped directly to gas phase reactions.
Let's actually double-click on that gas phase reaction one. This paper by Millard, Zhao, and Pedersen is a perfect example. They show how probabilistic sampling can literally map the completely chaotic kinetics of gases. Think about it. Gas molecules are zipping around at incredible speeds in totally randomized, unpredictable directions. Trying to model how they chemically react using standard, rigid numbers, pretty much impossible. But by applying this probabilistic method, they can navigate through all that uncertainty and accurately model those chemical reactions exactly as they happen. So, where does this all lead? Let's take a look at the future of applied math.
This one honestly might be my favorite. Just look at this paper title from the 2025 conference by de Suster, Colmont, and Lee, Solving Einstein's Equations as Bayesian Inference. They are fundamentally reframing the very fabric of Einstein's equations through the lens of probability. We all know Einstein's equations of general relativity are famously complex, and solving them numerically is notoriously difficult. But here's the genius part. By treating the solution not as a strict, rigid calculation, but as an active Bayesian inference, meaning they continuously update their predictions as they get new evidence, they're opening up entirely new ways to simulate black holes, gravitational waves, and literally the expansion of the universe itself. Which really leaves us with this final provocative thought. If injecting uncertainty into math can help us decode everything from aircraft turbulence to the literal equations governing spacetime, what mysterious corner of the universe is probabilistic numerics going to paint a clearer picture of next? Because from the vibrations of a suspension bridge to the firing of our neurons, all the way to the fabric of reality itself, this field is proving one profound thing. Acknowledging exactly what we don't know might just be our greatest tool for discovery.